Chapter 3, Part 2, Equipment Sizing. Pipe sizing. The universal hydronics formula is used to calculate the correct pipe size, circulator, and heat transfer for each room. The universal hydronics formula states that gallons per minute equals BTUs per hour divided by the design temperature drop, also known as the delta T, times 500. Fin tube baseboard has a design delta T of 20 degrees Fahrenheit. This means that water enters the zone at 180 degrees Fahrenheit and returns at 160 degrees Fahrenheit, 20 degrees cooler. Most residential radiant floor heating systems have a design delta T of 10 degrees. Water enters the loop at 130 degrees and returns out at 120. A larger delta T might mean a noticeable drop in floor surface temperature near the end of the run. Now let's try an example where the heat load required is 70,500 BTUs per hour. It's going to be delivered through a zone of baseboard, and we need to know what size piping will be required. So starting with the universal hydronics formula, which states that the gallons per minute equals the BTUs per hour divided by the delta T times 500. Now in our case, the BTUs per hour is 70,500 and the delta T is equal to 20 degrees. So 70,500 divided by 10,000, which is 20 times 500, or delta T times the universal formula factor of 500, that equals 7.05. Now we're going to round that up to 7.1, and that equals the gallons per minute we will need to move water through this structure to get the proper heat distribution. The rules of thumb for pipe sizing are: for 2 to 4 gallons per minute, you will need a 3/4 inch pipe. For 4 to 9 gallons per minute, you'll need a 1 inch pipe. For 8 to 14 gallons per minute, you'll need 1 1/4 inch pipe. And for 14 to 22 gallons per minute, you will need a 1 1/2 inch pipe. And since 7.1 gallons per minute is required in our example, a 1 inch pipe will suffice for this application. This section will address circulator sizing. Before a circulator can be selected for a particular application, both the flow rate and the pressure loss due to friction in the piping must be considered. The circulator needs to produce the required amount of flow while overcoming that pressure loss. In hydronics, this pressure loss is typically referred to as head or head loss. Pressure is generally measured in pounds per square inch, or PSI. And to convert PSI to head loss is quite simple. First, you know a column of water 28 inches high, or 2.31 feet, has a gauge pressure at the bottom of 1 PSI. Therefore, 1 PSI of pressure drop in a system equals 2.31 feet of head. The height of the building is not considered when sizing a circulator. The circulator doesn't lift the water to the top of the system. System pressure does that. The circulator only overcomes the head loss. To determine the head loss of a zone, measure the total length of the zone, including both piping and heat emitters. Fittings and valves produce additional pressure drop in a system, so the total length of the system is multiplied times 1.5 to calculate the total developed length of a zone. Next, multiply the total developed length by 0.04, which representing 4 feet of head per 100 feet of copper pipe. Let's do a sizing circulator scenario exercise. So first, in this scenario, our zone has 27,000 BTU per hour of baseboard, a length of 45 feet, and a developed length of 80 feet. So we need to determine the flow rate and the head loss. First, we need to find our flow rate. So let's remember that flow rate is determined by using the universal hydronics formula. And to review, the gallons per minute is achieved by the BTUs per hour divided by the delta T times 500.
So in this case, we have 27,000 feet of BTU baseboard. We divide that times our delta T of 20 times 500. This gives us 2.7 gallons per minute flow rate. Now we need to determine our head loss. So let's review. Determining the head loss by measuring the total length of the zone, multiply that times 1.5, and that gives us the total developed length. Multiply that times 0.04, and that'll give us our head loss. So in this scenario, we have 80 feet of total developed length. We're going to multiply that times 1.5 and then times 0.04, as our formula states. This is going to give us 4.8 feet of head. So now we know we need a circulator that can provide 2.7 gallons per minute of flow and overcome 4.8 feet of head. Now we go to our sizing circulator chart. So remember, we need 2.7 gallons of flow and we need to overcome 4.8 feet of head. So plotting this on the chart, you will see that circulator number 3 falls within this range. Therefore, in this application, the ideal circulator is circulator number 3. 3-speed circulators are designed for a wide range of flow and head requirements. These same calculations are used as with a standard circulator. In this situation, the setting would be on low speed. When one circulator is serving multiple zones, the flow rate requirements and head loss for each zone must be determined first. Then, to find the total flow rate, add all of the zones together. To determine the total head loss, use the largest head loss. The gallons per minute is cumulative, head loss is not. If a circulator can overcome a high head loss zone, it can overcome a lower head loss zone. Let's look at a case where we have two zones in the system. Zone 1 calls for 2.5 gallons per minute flow rate and a 6-foot head loss. Zone 2 calls for 3.5 gallons per minute flow rate and a 4-foot head loss. So we need to add the gallons per minute for each of the zones together, which will give us 6, but we only need to choose the largest value for the head loss, which is 6 foot. So in this case, our circulator demand is 6.0 gallons per minute with a 6-foot head loss. There is an additional factor that must be considered when determining the total head that a circulator may need to overcome, and that is the components within the system itself, zone valves and flow valves. They each have a head loss. And again, these must be considered when calculating the total head. So we do that by starting with the coefficient of flow. And that is the pressure drop through a component which is equal to 1 gallon of water flow at 1 psi pressure drop. So for example, a component with a CV of 3.5 and with a 3.5 flow will cause a pressure drop of 1 psi. Now the higher the CV rating, the lower the pressure drop is. So we come up with the head loss for the component using this formula, which is flow divided by the CV factor multiplied times itself, or squared, times 2.31. Let's take an example. Using our scenario of just a few minutes ago, where we had two zones, and the second zone had a 3.5 gallon per minute flow rate, we're going to be putting a zone valve in there that has a CV of 3.5. Now the CV is not something you would need to calculate. That is a number that is provided in the specification sheet of all the zone valve manufacturers. So using our formula, which is flow divided by CV squared times 2.31, will give us our head loss for the component. In this case, it's fairly easy. We have a 3.5 gallon per minute divided by 3.5, which is the CV, and that gives us a value of 1. 1 times itself, or squared, is still equal to 1. We multiply that times 2.31, and that gives us a total head for this zone valve of 2.31 feet. A few moments ago, we discovered we had a 6-foot head loss on our piping. We need to add the higher of the head loss factors from our zones. In this case, it's zone 2, and our factor is 2.31. So going to take the 6-foot head loss from the piping, add the 2.31 head loss from the highest zone head loss, and we come up with an 8.31 factor. So the total head loss, including both the piping and zone valves, is 8.31. Therefore, you need to refer to the circulator's sizing chart to find the correct size or setting for this application. When sizing expansion tanks, it's best to use the tank manufacturer's guidelines because sizing recommendations vary based on the type of heater meter in use. However, if the manufacturer's instructions are not available, the rule of thumb for the minimum size tank is as follows. For diaphragm tanks, it's 1 gallon per each 7,000 BTUs per hour of heat load. And for steel, it's 1 gallon per every 5,000 BTUs per hour of heat load.